Okay, so we're ready to actually tackle our last derivative rule, and that's the rule for the derivatives of the logarithmic functions. I say the last differentiation rule. We're actually going to look at a technique of finding a derivative of a particular type of function, which will actually involve logarithms, but that's something we will do here shortly. First, let's start with recalling about the logarithmic functions. So remember, those are the inverse functions to the exponential functions, and so the domain of the log functions is everything greater than 0. That matches the range, if you remember, of the exponential functions. And the range of the logarithmic functions is all real numbers, which matches the domain of the exponential function. So remember how we write that, the log functions, log, and then the subscript a. There's exceptions, of course, to this notation. If it's log base e, we use ln, right? If it's e, so log base e of x, we would write as ln of x, ln. That's the natural log function. And then there's another one. If you have log base 10, that's sometimes called the common logarithm. A lot of times you'll see that without any subscript at all, just log of x, that's base 10. That's the way we do it, at least in the United States. Some other countries have some different other notations for these, but this is what we use. Okay, so but in general, a can be, again, any, remember, base greater than 0, not equal to 1. If the value of a is greater than 1, the logarithmic function is increasing on its domain. If the value is between 0 and 1, the logarithmic function is decreasing on its domain. Notice both functions have an x-intercept of 1, 0, because the log base a of 1 is always 0, since a to the 0 is equal to 1. So remember the relationship, y is equal to log base a of x means that a to the y is equal to x. Right? This is the logarithmic expression. This is the exponential expression. So remember, logarithms are exponents. So when I say log base a of x is y is the logarithm, y is an exponent. It's the exponent on what? The base. So if I take a to the y, I'm going to get back to x. Okay? They cancel each other out. Another way of thinking about it, if I plug x into the log base a function, the output is y. Take y and plug it into the exponential function, and get back to x. Okay? So the way I'm going to find the derivative of y equal log base a of x is using implicit differentiation. Since y equal log base a of x is equivalent to a to the y equals x, I'm simply going to take the derivative with respect to x of both sides of this equation. Okay, this side is the easy side on the right. The derivative with respect to x of x is obviously equal to 1. All right. What about this thing? This is the rule that we just looked at in the last video. This is involves the exponential function with base a, the general exponential function. But notice I'm taking the derivative with respect to x. It's a to the y. Y is a function of x. So this is chain rule, right? This is chain rule, and the outer function is a to the y. The inner function is y. The outer function a to the y, right? We know how to find that by the general exponential function rule. That's natural log of a times a to the y. And then times what? Times the derivative of the inner function. What's the inner function? Y. So what's the derivative of y with respect to x? dy dx. Right? So it's chain rule. And we're trying to find dy dx, right? Y is equal to natural log, log base a of x function. So what is dy dx? Well, here it is. To get it by itself, I'm going to divide by all this stuff. So we have dy dx is 1 divided by the natural log of a times a to the y. So again, when we use implicit differentiation, as typically happens, we'll get our derivative y with respect to x is a function of, in this case, just y, but we can get x and y in there. I would like it to be just in terms of x, right? Because my original function y is log base a of x. I would like that to be our the variable for our derivative. And I can do that because remember, what is a to the y? A to the y is just x, right? So a to the y is what we started with being equal to x, right? That's what we did there. And I can use that now to rewrite this as simply 1 over natural log of a times x. And so we have our rule for the logarithmic functions. The derivative with respect to x of log base a of x is 1 over natural log of a times x. There it is. Let's look at the special case when we take the derivative with respect to x of natural log of x. So what is natural log of x? That's log base e, right? Log base e. So another way of writing this is the derivative with respect to x of log base e of x. And so a is e. I get 1 over natural log of e times x. But the natural log of e is what? What's the power of e needed to get e? 1, right? Natural log of e is 1. So this is just 1 over x. Okay, so since the natural log of e is 1, this is the one logarithmic function whose derivative is just 1 over x, right? Since the log base a is equal to 1 in this case. If I take the derivative with respect to x of, say, log base 8, I'm just making that up, log base 8 of x, then by the rule this is 1 over natural log of 8, that's the base, times x. So there's our rule, and it is helpful to know this rule as well for the general, for the natural, rather, exponential, natural logarithmic function. Okay, so that's our last, quote-unquote, last rule. We're going to do one more technique here, but let's throw this rule, these two rules basically, into the mix of all the ones that we have up to date and see if we can find some derivatives here. So let's differentiate y equals t times the natural log of t. Okay, so what do I have here? T times natural log of t. What rule do I have to use here? Product rule. Right, I've got a product, I have to use product rule. And when I take the derivative of the product rule, I'm going to have the rule for our new logarithmic functions, right? Because I've got natural log of t. So y prime is the derivative of t times natural log of t plus t times the derivative of natural log of t. So that's the product rule. What's the derivative of t with respect to t? That's 1. What's the derivative of t with respect, or natural log of t with respect to t? Well, that's the rule we just developed, if you remember. And so what did we say? Here, of course, the variable is x. The derivative with respect to x of natural log of x is 1 over x. So the derivative with respect to t, natural log of t, is 1 over t. And then when I simplify, notice what happens. 1 times natural log of t is natural log of t. What happens here? T times 1 over t? T times 1 over t? That's just plus 1. Just plus 1. Okay. Let's look at this next one. Here I'm finding the derivative and of y. It's the natural log of cosine of x. Not a product, but a composition. Chain rule, right? Outer function, natural log of u, inner function, u equal cosine x. So this is a chain rule. And the inner function, we said, is u is cosine of x, and the outer, y equal the natural log of u. So how do we do the chain rule then? The derivative of the outer function, right? What's the derivative of natural log of u? We just said it's 1 over u, where u is what? U is cosine of x, times the derivative with respect to x of the inner function u, cosine of x. What's the derivative with respect to x of cosine of x? That's negative sine of x, right? Negative sine of x. So I get 1 over cosine of x times negative sine of x. That's negative sine x over cosine x. There's our answer. Does anyone see something that we could do to rewrite this maybe a little bit simpler? I hope it jumps right out at you. A trig identity, very important one. The ratio identity, right? Sine x divided by cosine x is equal to which trig function? Tangent x. And so here's a thing. We've found a function whose derivative is negative 1 times tangent x. So in other words, if I were to take the derivative of negative, the natural log of cosine of x, the derivative would be equal to positive tangent x by the constant multiple rule, which is kind of neat because we know how to find the derivative of the tangent function, but we didn't know what function I take the derivative of to get the tangent function. And so that's going to be a process you'll be going through in Calculus 2, and so this is actually a helpful problem to see that. Okay. Let's move on. What about the derivative of the function g in this case? Well, this is the square root of the natural log of x. Well, I would first of all write this as the natural log of x to the what? 1/2 power. So this is a composition. I've got the going to use chain rule, right? The inner function is what? U is the natural log of x, and the outer is what? Y or g of u is what? U to the 1/2 power. So it's chain rule. So g prime of x. Derivative of the outer function, u to the 1/2. I do 1/2 u to what? Subtract 1 from 1/2, negative 1/2. And what's the inner function? U, natural log of x, times the derivative with respect to x of the inner function. This is our new rule, right? We've been learning the derivative of the natural log function is 1 over x. And so what do we get? We get 1/2. This is what? 1 over the square root of, right, this right here is 1 over the natural log of x to the 1/2 power, which I can then write, if I want to, it's just the square root of natural log of x. So I've got 1/2 times this times 1 over x. So everything up top is 1, 1 times 1 times 1. And here I get 2x, and I'll put the square root of natural log of x, or natural log of x to the 1/2 at the end. Just multiplying those three denominators together, because I'm multiplying everything together. And there's my derivative. Okay. Now number 4, the 1 through 3 was all involving the natural logarithm, log base e. This function, right, h of t, is log base 3 of t to the 4th plus 5. So let's find the derivative by what? Chain rule, right? So the inner function u is t to the 4th plus 5 is the inner, and the outer is what? Y equal log base 3 of u is the outer. We've got chain rule. So h prime of t, what's the derivative of our outer function, log base 3? So that's that new rule, right? And we found that to be what? Log base a of x derivative is 1 over the natural log of a times x. Okay, 1 over the natural log of a times x. And so this becomes 1 over natural log, what's our base in this case? Natural log of what? Base is 3. Natural log of 3 times u, and u is what? T to the 4th plus 5. Times what? The derivative of the inner function, which is with respect to t, t to the 4th plus 5. So derivative of the outer function, evaluate the inner, times the derivative of the inner. That's the chain rule. So what is the derivative with respect to t of t to the 4th plus 5? That's an easy one, right? That's just power rule. Just power rule, 4t cubed. And so our derivative becomes 4t cubed all over the natural log of 3, let's put that in parentheses, times t to the 4th plus 5. Keep in mind, natural log of 3 is just a real number you can evaluate. The natural log of 3 is, again, is the power of the base e needed to get 3. E to what power equals 3? And the answer is natural log of 3. There it is. Here's our derivative. I just want to take a look at this function here. This will be basically, again, kind of anticipating something you'll be doing in Calculus 2. We know that the derivative natural log of x is 1 over x. And so when I look at the function, the natural log of absolute value of x, I can think of that as a piecewise defined function. It's just equal to the natural log of x if x is greater than 0. Because if I take the absolute value of any positive number, right, I'm going to just get that number. So the absolute value of 3 is 3, absolute value of 4 is 4, and so on. If x is less than 0, because again the natural log function is not defined for any values less than or equal to 0, so how can I plug in something less than 0? Well, it's the absolute value. So when I take the absolute value of negative 3, what do I get? 3. Absolute value of 4, or negative 4 is 4. Absolute value of negative 10 is 10. So what's another way of doing that without the absolute value? Well, how do you change a negative 10 to a 10, or a negative 3 to a 3, or a negative 4 to a 4? One way, you can multiply by a negative 1. Right? So if x is less than 0, negative x is going to be greater than 0. Right? And so this is a piecewise defined function. And when I talk about the derivative, if x is greater than 0, we already know that f prime of x is just the derivative natural log of x is 1 over x. Right? If x is less than 0, what's going to happen though? F prime of x then is the derivative with respect to x of what function? Well, the natural log of negative x. And what do we have here? This is a chain rule, right? This is a chain rule. And the inner function, very simply, is u is negative x. U is negative x. And the outer is y equal natural log of u. And so the derivative of the outer function, natural log of u, is 1 over u, and u in this case is negative x, times the derivative with respect to x of the inner function, negative x. But what's that? That's just negative 1. So 1 over negative x times negative 1 is, again, positive 1 over x. And so what do we observe? If x is greater than 0, the derivative is 1 over x. If x is less than 0, the derivative is 1 over x. And so what we have is that the derivative with respect to x of the natural log of the absolute value of x is 1 over x. And that'll be important for Calculus 2. Nice way to extend the log function to negative values, essentially, is to consider this function here. And its derivative is 1 over x. Of course, that's only true for all values in the domain, which is what? Everything that is what? Not equal to 0. Okay. So we've developed our last two derivatives. I did want to look at one thing real quick, though, before we move on, and that is just looking at the logarithmic function in general here. All right, if I'm taking the derivative with respect to x of the natural log function, and u is some function of x here, this is chain rule, right? So this is going to be what? 1 over u is the derivative of the outer function times what? The derivative of the inner function, du dx. Okay. Now du dx, derivative of the inner function, is sometimes written as u prime, and so we can think of this as u prime over u. And that's a nice way of remembering the derivative of natural log of u. It's just the derivative of the inner function over the inner function. So in other words, if I'm taking the derivative with respect to x of the natural log of x cubed plus 3x plus 2, right, then what's that going to be? Well, by this rule, the inner function here, notice, is what? U equal x cubed plus 3x plus 2. Well, so by this rule, what's u prime? What's the derivative of x cubed plus 3x plus 2? That's 3x squared plus 3 over what? U, which is x cubed plus 3x plus 2. So that's a quick way to remember the derivative of natural log of u is just u prime over u. Okay. So we're going to stop here with this video, but in the next video we are going to take a look at a method of differentiating functions where both the exponential functions actually, where both the base and the exponent are variable. Both the base and the exponent are variable. It's not the power rule, because the power rule needs the exponent to be constant. And it's not the general exponential function rule, because there the base needs to be constant. So what do we do if both the base and the variable are, base and the exponent are variable? Well, we're going to use a method known as logarithmic differentiation. And so as the name implies, we're going to use the logarithm, and in particular the properties of logarithms, to simplify the problem and then take the derivative. So we'll look at that next.